Hello, in this video, our relativity adventures continue as we talk about the fun math of Lorentz transformations. Remember those good old Galilean transformations? Those were the days, huh? Well, they don't work when we get close to the speed of light, so we got to make some adjustments. Here they are, and we'll talk about them. It's a bunch of equations in your data booklet, so we're just going to look at what they are and how to use them. Okay, so first thing is, why do we even bother with the Galilean stuff if it's not accurate? Well, it is pretty accurate for our everyday life, and here is some justification of why. All right, so these good old, the first two in the data booklet, the good old simple, just add the velocities and so on equations, do work at low speeds because essentially we're going to look at the equations in a second, but you kind of multiply these by a Lorentz factor, more or less for the first one at least. All right, so you can see the Lorentz factor is kind of a factor of how much time gets dilated by, right, for example, and all kinds of things like that. So if the Lorentz factor is 1, we're really not having any relativity effects. And so, all right, this is something called beta. You might see it from time to time. It's called the speed parameter. It's a ratio of the speed of one reference frame to the other compared to the speed of light. So beta being 0.2 would mean like reference frame S prime is moving 20% the speed of light. 40% the speed of light, 60% the speed of light equal to the speed of light. Okay, and like we're seeing a little bit with the time dilation already, until you get very close to the speed of light, the gamma is pretty small, the Lorentz factor is pretty small, and the difference between like 98% the speed of light and 99% the speed of light is really big. So there's a difference between like 99% and 99.9%. But the difference between like 10%, 20%, even 40% is not much, and there's really not much happening here. The Lorentz factor is pretty close to 1, which means we don't have to worry about relativity stuff, or we're going fairly slowly, even pretty fast. 10% the speed of light is quite fast for everyday life, faster than anything we're dealing with usually on Earth is going to be moving in our regular good old classical mechanics. So the Galilean equations and all the other physics that we learn is very good. A good rule of thumb is like below 10% the speed of light. So what, below 30 million meters per second? Yeah, so they're very, very good for everyday life. But when things are going near the speed of light, we need some updated equations that were developed by Lorentz. And there's lots of fun math that goes into them. And then they just show up in your data booklet. So here they are. Really, what it's going to come down to is knowing these equations and when to use them, as always. So Lorentz took postulates of special relativity and some of the work from Einstein and so on, and smashed together some math to come up with these transformations. So these kind of replace our x and t transformations for Galilean stuff. All right, so here's our new transformation equations. We got a good old x prime one in terms of x. So this will give us our, same as always, the primes are in terms of the s prime. Usually we say moving reference frame. The not primes are in terms of like s not moving reference frame. I got my Lorentz factor is the same as before. So we use that good old 1 over square root 1 minus v squared over c squared thing, also in the data booklet. Yeah, and I tie all these things together. So I got x's and x primes. I got t's and t primes. The main thing is going to be keeping these straight. One fun thing to point out is that when we come up with a new theory like this, when we come up with something crazy like saying, hey, you can't just like add velocities together, even though we've been doing that for hundreds of years and it's worked great because we weren't going close to the speed of light, these need to still account for that. These need to simplify down to the Galilean equations when we're in everyday life, when v is like way less than the speed of light. Right? So picture what happens to these if v is way less than the speed of light. Well, this becomes 1. The Lorentz factor becomes 1 at very, very low speeds, right? And so imagine if this is 1, then I just get x prime equals this. That's our Galilean equation, yeah? So that's the normal one. This still works and gives me the same answer as Galilean. It just also accounts for if I'm going real fast, I scale things appropriately. Same for the time one, which is even more fun. This would become 1, but also notice if v is way less than c, right? If this is way smaller than c, this term is practically 0 compared to this. In other words, this fraction is very, very small, almost zero small, and I do get t prime equals t. Our original assumption about time is the same for everybody. Well, it's not, but it basically is, as long as you're not going more than like 10% the speed of light relative to something else. Okay. All right, so those are two equations of just how to do these transformations. We're going to practice some with them. The one thing that the data booklet doesn't give you is what's called the inverse transformation. So this gives me x prime in terms of like x and t. So, but what if I want to find like x? Or what if I want to find t? It's not quite as simple as solving these because a lot of times I don't want to deal with the t or the x. So we have these. So the data booklet is about position and time in the S frame relative to S. But if I want to find position or time in S relative to the prime, and I want like all my prime stuff, I have to come up with two other equations. So write these down, and what you really want to do is commit these to memory. And there's a pattern of how you can get them from the data booklet equations. That's not too bad. You do this. All right, but because I want x in terms of x prime and t prime, I can't just use this because I got a t and an x prime. So there's some fun substitution you can do to derive those, but that's not something you would want to take your time doing on an exam or something like that. So notice the pattern. Here I got x prime gamma x vt. Here I got x gamma x prime vt prime. Really what you're going to do, it's the same deal here. You just kind of flip the primed and unprimed quantities, I'm calling it, and flip the sign of the relative v. So again, the first equation was, it would be x prime equals gamma times x minus vt. So what we're doing, what it really works out to is, you take your x prime, turn it into x, your x turns into x prime, the minus a plus, and the v is the same because v is, defines kind of the relationship between the two frames. We don't ever have a v prime. Gamma stays the same too, and I swap t for t prime. All right, so you flip, here's how you do it, because you will need these. You flip the primed and unprimed things, and you flip the sign from negative to positive, and it all works out. All right, if you want to go on Schoology or Cognity and look at the fun derivation of all this stuff, it is there if it helps you understand. But again, not something you're going to really have time to do, so you just want to get in the habit of doing this. Same deal here. The other equation was t prime is gamma times t plus v prime, I guess, right? X, oh no, there's no v prime. Vx prime. So it's going to be vx. So it was t plus vx over c squared, yeah? So those are my two equations before, yeah? And same deal, what I'm doing is I'm flipping the primes, but not primes. T prime becomes t becomes t prime, x becomes x prime, and that was a minus, so I flipped the minus to a plus. Okay, so that'll take some practice, but you want to be able to do that to go to the inverse transformations. That is a tricky one that you do have to more or less memorize, that you have to do this. But again, just use this rule of how to get them, and it'll get you there. Okay, and there is another one for velocity addition. Just like we had a velocity addition, nice easy one in Galilean, well, we got a more complicated one here. Okay, so here it is. This is velocity addition when we're dealing with relativity. It's a little funkier with the math derivation, but this is what we end up with. All right, so it's u prime in terms of u and v. And if I want to go the other way, I do the same inverse thing. All right, so here's the equations, and what we're going to do is just practice with them, because that's what will help, is when you see and do it, happening. We can just point out this, again, should simplify down to the Galilean equation. And again, if v is way less than the speed of light, then what do we get? This should become 0, basically, because v is going to be way smaller than c, so this fraction is really close to 0. I get u prime equals u minus v over 1, which just means u prime equals u minus v, which is our first Galilean velocity addition equation. All right, so you only use this if you're going close to the speed of light, and then you have some fun with fractions. There you go. And same deal. So this gives you u prime, the velocity of an object in the S prime frame in terms of the S frame. All right, common thing is like a ball rolling inside of a train or something like that. And we have weird physics problems, super fast speed of light trains. Um, but I might know how fast the ball is going relative to the ground and the relative speed of the frames, and I want to find how fast the ball is going like in the train. But if I want to go the other way, which is pretty common, I got to do this. And it's the same thing. You flip the primes and not primes and flip the minuses to pluses. So I take if I want instead of the u prime equation, if I want to get u, I would flip this, flip the u to u prime, v stays the same, minuses to pluses, and flip this u for a u prime. All right, so again, that's going to take some practice. You do need to be able to do that. It's a little annoying that it's not on the data booklet, but here we go. All right, so let's put some of these equations to work so we can see how they work, because doing the math and doing a bunch of practice with these is really what you got to do to start to understand and get comfortable with the weird transformation stuff. Okay, so an experimenter arranges to trigger 2 flash bulbs simultaneously, providing a big flash at the origin of their reference frame and a small flash 30 kilometers away. An observer moving at a speed of 25% the speed of light is moving in the positive direction of x and also views the 2 flashes. What is the time interval between the flashes? Okay, so for the experimenter, let's set some stuff up. We always want to think carefully about, okay, what's our S frame? What's our S prime frame? What kind of primes and not prime quantities are we dealing with? And we'll use that to help us pick our equation. All right, so let's say I'm thinking the experimenter is going to be the S frame. We kind of got an experimenter like just on the Earth, I guess, at rest. And then somebody's zipping by at 25% the speed of light. So the observer, let's call it the S prime frame. Okay, that's nice because we have X here. That's what I would want this to be because that's X in terms of the S frame. All right, so this will be V. It's in the positive direction, so it is positive 0.25 C. Also use the 2 flashes. I want to find the time interval according to the observer, which time according to the observer. So I want time in the S prime frame, which would be T prime. Okay, so I want T prime. There's one other thing I can infer here because of this word simultaneously. Remember, there's no such thing as like absolute simultaneity. The idea here is that while the 2 events happen at the same time for the experimenter, they don't for this person. Crazy. But if it's simultaneous, then for the experimenter in the S frame, the time between the 2 events is 0. That would be what simultaneous means. So I know T, the time between the 2 events here. Okay, so I want to find the new time from the old time. So I got a T, I got a V, I got an X. I want to find T prime. So I go to my big list of crazy equations. And as, hairy and complicated as this stuff is, when it boils down to it, I'm just doing some guess method math. Because there is an equation that relates all of this stuff, which is T prime equals Lorentz factor gamma times T minus V x over C squared. That's the equation. It's in the data booklet. So if I can just identify these things and name my S and S prime stuff, name my regular and primed quantities, I can pick an equation that's going to get me there. This one's already solved for what I want. Because I know T, that's 0, so that's going to make this easy. I know V, I know X, then the speed of light's the speed of light, and this one I get just from the V. So I'm good to go. So let's do it. All right, I guess we can do this first. I know T is 0, right, from this guy. So this will simplify a little bit. T prime will be gamma times, don't forget this is there because I'm subtracting it from 0. So it's negative Vx over C squared. I'm going to get some kind of negative with my T. This is very fun. Okay, let's solve for gamma. This is always good to do sort of off the bat. So let's get our Lorentz factor. 1 over square root 1 minus V squared over C squared, right? So let's just do it all at once. 0.25 C over C. Let's do it this way too, which is also fair if you want to think of it like this. Yeah, because I'm squaring both, I can square the fraction. The C's go away. So I'm going to do 1 minus 0.25 squared and square root that. And then do 1 divided by that. Oh, Lorentz factor. So fun. So fun for the calculator. Anyway, make sure you can do that and your calculator skills are good and your order of operations and parentheses and all that, because you should get, it's not too big, right? 1.0327 96. Even so, only 25% the speed of light, which is very fast. It's still not very big, you know? Like time, for example, would be dilated 3% more. Okay. Anyway, there's our Lorentz factor. Let's now plug in stuff to the equation, yeah? Because now I got this, which is going to go here. I know V and X and C is a number in my data booklet, so let's do it. All right, so T prime is going to equal 1.03, blah, blah, blah. Really what I want to do is keep this in my calculator and then do all this and then multiply it by this number in my calculator. Ideally, I don't round anything until the very end of the problem. But honestly, if I keep something crazy like 5 decimals for a 2 sig fig problem, I'm going to be good. Okay, so negative. All right, then V is 0.25 C. Then X was 30 kilometers. So be careful with kilo as 10 to the 3 meters. Is how I'll do it. All right, I got my V times X and I divide by C squared. This is one where I do have to plug in a value for the speed of light. A lot of times we're just like using C's and canceling stuff out. But in this case, you know, I got one C. I guess I could. I can do this if I want, right? Because that's 0.25 C. That's C squared. So one of the C's cancels out, right? Which means I'm really dividing by, I'm going to be floppy and do this all at once. I'm really dividing by 3 times 10 to the 8 meters per second, the speed of light, because I got 2 C's down here, 1 C up here, so they cancel out, right? So I end up with just 1 C. Yeah, or multiply by 3 times 10 to the 8 here, and call this 3 times 10 to the 8 squared, same thing. Anyway, calculator, 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 plug all that in. Don't forget this, you do get a negative number. You get negative 2.58 times 10 to the minus 5 seconds. Oh boy. We can be fancy because 10 to the minus 5 is pretty close to a prefix of 10 to the minus 6 for micro. So I am thinking that would be negative 25 or 26 microseconds. Negative 25.8. I move the decimal over here to make it an extra one. So let's just round it now to 2 sig figs. Because, oh no, 3 sig figs. We do get 3 sig figs. Yeah, 3 here, 3 here. So yeah, we keep 3. Okay, so negative 25.8 microseconds is what I'll say. You could just call it this. This is also perfectly fine. Okay, negative 25.8 microseconds. I wonder the time interval between the flashes. So to me, that actually implies I don't need the negative in this answer. So let's drop it for now because it's 25.8 microseconds between the events. But the fact that the negative is there is important for this. All right, so this is a crazy concept, but you know, the bulbs were simultaneous for the person in the experiment, but there's some time difference between the events for the observer. The fact that we got the negative, well, what did we plug in? We plugged in 30 kilometers for X. So we're really finding the time, we're in other words assuming that, and it's true, T prime for the first flash will also be 0. That's like occurs at time equals 0 if you want to think of it that way. When I plug in 30 kilometers, which is what I'm doing here, I'm finding like when this flash happens, the small flash relative to the big flash. So the time of the small flash in terms of the big flash is negative, which means it happened before. It's not like going back in time or anything that crazy. It's just telling us one event happened before the other. Since this one's a negative time compared to this, this event happened before the other. So the first one was the small flash because I got a negative answer. So the small flash happened 25.8 seconds, microseconds before the big flash is why I got a negative. All right. A weird concept, but there you go. That's how you use one of these. So again, as always, it looks pretty hairy, but we're just identifying our variables, picking an equation that will work, and then go from there and try your best to think about it. But these definitely will take some practice. Here's another we can practice. All right, this is a relative velocity one. So I got a spaceship traveling at a speed of 80% the speed of light relative to a ground station in frame S. Probe on the spaceship moves towards the front of the ship with a speed of 0.5 c relative to the ship. What's the speed of the probe relative to the ground station? Oh, man, great. All right, so I got a spaceship. I think a sketch will be good for this. My beautiful spaceship here. The spaceship is moving 0.8 c. That's going to be v, right? That's like relative to a ground station of frame s. So that's my speed relative of s prime relative to s, where s prime is going to be my spaceship. So let's label this. Okay, now I got a probe moving towards the front of the ship. So inside of here, there's like a little probe. And here goes 0.5 c forward relative to the ship. So what should that be? Think about it. Is that u or u prime? It's the speed of an object. And since it's relative to the ship and the spaceship is s prime, that is u prime. U prime. All right, so this number, I'm going to do this. This number is u prime is what they gave me. That's important. It's like very easy to mix these up and call that u or something like that. So always think about what frame is this measured in. So that's u prime. So if you're inside the spaceship, you see this little, probe droid going towards the front at half the speed of light. And what is the speed of the probe relative to the ground station? Well, speed of the object relative to s is u. That's what u is defined to be. Okay, so what is u is the question. All right, so now I look at my situation. I need to find u, regular u, when I have u prime and v. Well, if I look at my data booklet equation, the first one, like the regular velocity addition in there, is not great because that one is like u prime in terms of u and v only. What I need, though, is to find the u equation. Like, in other words, I don't want to go back for a second. I don't really want to use this one to solve for u because I have two u's here. And it's going to be a mess to, solve for that u. Why don't I just use the inverse one? The one where I solve for u in terms of the u prime and the v and the c, which is all stuff I know. All right, so this is where this comes in really handy. If you just use the data booklet equation and try and solve for u, you're never going to finish if you're just doing algebra on the exam. So remember that the inverse is a thing you can do. And let's do it. Again, now if I know to use that equation based on what I got, it's, fairly easy. Just plug and chug now. So, all right, the u that I want is going to be u prime plus v. Watch that we flip all these minuses to pluses for the inverse, right? Over 1 plus u prime times v over c squared. Oh, fractions. All right. Let's plug in numbers and see what happens. So u prime plus v. So I got u prime is 0.5c plus v is 0.8c. Are we able to combine those? They're like terms. Over 1 plus u prime times v. So now I multiply these. 0.5c times 0.8c. Don't lose the c's. This is important. Over c squared. Well, good news. I don't have to plug in speed of light for these because I got c times c up here over c squared. All that stuff goes away. And then I'm going to get an answer in terms of c, if you can see it. All right, so let's carry through, though. Add these together. 0.5 c's and 0.8 c's gives me 1.3 c's. And then divide by 1 plus 0.5 times 0.8, which is going to be, I'm thinking 0.4. 5 and 8 is 40. So I get 1.3 c over 1.4. I'm immediately doing a mental check. This makes sense to me because I have to have an answer less than c, right? This fraction has to be smaller than 1 because nothing can ever go faster than the speed of light. If you get an answer that like your object was moving at 1.1 c or something, you did it backwards, you did it wrong, you want to go back and check. You'll never get something faster than the speed of light. So all I do is do 1.3 over 1.4. And I got like 0.92857. We'll round that to 2 sig figs. And so our probe is moving relative to the ground at 93% the speed of light. All right. So there you go. That's a inverse velocity one. Okay. Yep. Again, same old story. Know your equations, be able to identify the variables. As crazy as it gets, that's what we're doing. Okay. Couple more things. All right, this is going to be a long one, but there's one more basically thing that we will talk about, an equation in the data booklet that we'll set up here. And we can start it with an example. This one is a little simpler. Okay, but let's say you have an astronaut, a very qualified astronaut on the space station who saves the day with an inanimate carbon rod, 44 centimeters in length. If an observer is flying past the space station at the same time, parallel to the rod, that part is like important because this stuff is always in one dimension, at a relative speed of 83% of the speed of light, what's the length measured by the observer? Here's one key thing. There's going to be a lot of length stuff. In fact, there's like a length equation in the data booklet, so we deal with length a lot in relativity too, which is where we're leading with this. When you measure length, by definition, you have to take the measurements simultaneously. Otherwise, you're not measuring a length, really. All right, so lengths always have to be measured at the same time. So, all right, what do I want? I really want to find like x prime, I'm thinking, because on the space station, we're going to say is s. We're going to say the observer flying past is the s prime. So that would make this x. Regular x is 44 centimeters. Kind of officially the position between two events, the events being the left end of the rod exists and the right end of the rod exists both at the same time. We're like e equals 0. But we want to do it in the t prime. So what we want is x prime, and we need it to be at the same time in this reference frame as well. So I need t prime to be 0, and I need to find, whoops, x prime equals what? I need to find x prime when t prime is 0. That's really the idea. So what we're going to use is this equation, the inverse transformation. I'm thinking is the best thing to use because I know x, and I want x prime, and I have t prime. The other one's not great because I need it to be simultaneous in the prime frame, so I need the one with t prime so I can make this 0. Once I do that, this is pretty easy though. I need to solve for x prime. This whole thing is 0. So guess what? X prime is just x over gamma. X over the Lorentz factor. So I take my 44, divide by a Lorentz factor. Easy peasy. And okay, so same as always, we're going to do 1 over square root of 1 minus v squared over c squared. V squared is, v is 0.83c. Okay, so I'm going to skip a step here if we're cool with this, because this is always how it works out, right? Because I'm really doing 0.83c squared over c squared. So it's really this. And I plug all that in my calculator, and I get 1.79, blah, blah, blah. So what I do is I plug in 44 for x. I plug in this for gamma. I do 44 divided by 1.79, so on, and I get 24.5. So I get about 25 centimeters. Okay. All right, so that's to show you sort of where something comes from. You won't usually use this equation for this because this happens a lot. This is a common thing where we're measuring a length in one frame compared to a length in the other frame. The process of how you set it up is always the same. There's a bunch of ways you can set this up too. This one's a little sloppy, but it kind of gets the job done. But anyway, a length in one frame moving relative to another frame will always be less. Oh, it'll always be less. It looks shorter. So if you're flying by, the rod looks shorter to you. This is called length contraction, and it's kind of the other side of the coin of what we talked about before of time dilation. All right, so this is kind of the idea that we just set up. To measure length, you need the position of 2 points at the same time, you know, the endpoints. And simultaneity is relative. So will be length. And here's what it works out to be. When you measure length in a moving frame relative to the frame in which the object is at rest, you will always get something shorter. So that's called length contraction. So really, this is the equation we just came up with, that the length measured in the moving reference frame, which we'll call the contracted length, is equal to the proper length, the length of the object in the frame where it's not moving, the frame it's like stationary relative to, divided by the Lorentz factor. Okay, so another equation when we're talking about different lengths, this is the one you use. The length of an object measured in a moving frame compared to its kind of rest length, if you want, its proper length. All right. And just like with time dilation, this is a ratio situation. So you could do centimeters and centimeters like we did. You could do meters and meters. You could do miles and miles, whatever. Okay. So the final thing we have to say about this is this length contraction comes up as well in muon decay. And this is going to highlight the idea that length contraction and time dilation are kind of two different ways of looking at the same thing. So what the IB wants you to know is that muon decay is also evidence for length contraction. That's really what it comes down to, and I'll show you why. Essentially this, muons, one of the main places they come from, other than making them in a particle accelerator, is cosmic rays from space come crash into the atmosphere, molecules in the atmosphere, and as part of that, sometimes these muons get produced. They're way up there in the sky, and they can come flying down to Earth, but remember the muons are these things that have a really short lifetime, like 2.2 microseconds. And even though some will last more than one lifetime, that's like an average, it's very unlikely that we would get very many at all that reach the surface because it's so far and they can't quite get that far in their 2.2 microsecond lifetime. But we get a whole bunch, more than you would like expect. All right, so that's the main evidence, because here's what's going on. There's two ways to do it. And the one way we kind of did already when we did that lab question in the time dilation one, from the reference frame of, let's say, the Earth. Let's say these muons are formed like 9,000 meters up, and they only got 2.2 microseconds, and they're not going quite fast enough to cover that distance, really. But the muon has 2.2 microseconds of lifetime in its reference frame. We know, though, since it's moving so fast, to us, it's a much longer time. It was like 60 microseconds or something. So if I, view this through the lens of time dilation, that explains why they have time to reach the ground, because time is dilated for us relative to them, and they reach the ground. But does that make sense from the muon's point of view? Well, we got to think about the muon's point of view, which is so fun. If you're the muon, you do decay in 2.2 microseconds, but also this distance, since you're moving relative to the Earth, this distance is contracted. All right, to the muon, this distance, if I divide that 9,000 by the Lorentz factor, works out to be about 600 meters, which is a little shorter than the muon will go in. It's 2.2 microseconds. Everything gets contracted for the muon relative to the ground. And it's fun. The mountain here would be the same width because it's only contracted in one dimension, the dimension you're moving. You see this really short, wide mountain flying up towards you, only 600 meters of distance. All right, so the length contraction here accounts for the muons hitting the surface as well as the time dilation. All right, so they're really two parts of the same thing. You can kind of derive one from the other, so they really are mathematically two ways of saying the same idea. So the big takeaway you want to be able to say then when the IB asks you about evidence, muon decay experiments are one of our key pieces of evidence for both time dilation and length contraction. Either concept can explain how they reach the surface of the Earth from the atmosphere, even though according to classical physics, they shouldn't have time to do so. Okay, holy moly, that's a lot of physics. All right, so lots of fun Lorentz transformation equations. Again, they might look scary and intimidating, and they can be tricky, but it really just comes down to taking your time, being careful, thinking and visualizing your S and S prime frames, and what's prime and what's not, and then just going through your equation tool belt and picking what you can and slogging through the math, which is so fun. So do some practice. You will get more comfortable with it than you expect. Yeah, so get to it. Go practice and have fun.